Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosine River College in Sacramento, California. In this video, we're going to continue our discussion about double angle identities in trigonometry, and we're going to use them to solve simple trig problems here. And these are the most common ones you would see in a trigonometry course. In fact, some of my favorites. So we'll start with this guy right here. Let sine of A equal a negative 3 over 5, with A being in quadrant 3. And then we're being asked to find the sine of the double angle, the cosine of the double angle, and the tangent of the double angle. Rather than me going back to a previous page to showcase what that is, it is assumed that you've actually watched my theorem and proof of the double angle identities. But rather than going back to that page, I'm going to just get practice with you writing them out. So the sine of the double angle is twice the sine of the regular angle times the cosine of the regular angle. And then the cosine of the double angle has three forms. Its natural form is cosine squared of the angle minus sine squared of the angle. However, if you want to trade out that cosine squared for a 1 minus sine squared, then this would become a 1 minus sine squared, or 1 minus 2 sine squared. And likewise, you could have instead traded out the sine squared for a 1 minus cosine squared, and when you distribute the negative, you'll end up with 2 of the cosine squareds of A minus 1. Notice I don't bother writing the tangent of the double angle because I won't need it. I'm going to find the sine of the double angle first, then the cosine of the double angle, and then I'll take their ratio, and that will give me the tangent. That's why I never really bother memorizing the tangent of the double angle formula. Critical step to begin with here. Notice we're not given the sine of 2a, we're given the sine of a. And before I even begin, let me just tell you, this does not imply, maybe I should write it that way, it does not imply that sine of 2 times a is equal to negative 2 times negative 3 over 5. That is not true. You can't just say, oh, multiply both sides by 2 and bring that 2 inside the sign. That does not work. That just illustrates you don't know how functions work. So this is wrong. Bad. Don't do that. Okay. So instead, what you're going to do is just draw an angle that terminates in quadrant 3 because they told you A terminates in quadrant 3. So let's go ahead and start with that. Remember, the way I do trigonometry is with right triangles, really. So I go and open an angle all the way into quadrant 3, and it creates a right triangle. Right? You emanate a ray from the origin, and then at some point, doesn't really matter where, you stop drawing that ray, and then wherever you stop drawing that ray, just create an altitude back to the x-axis there. Now remember, this is right triangle trig, but obviously lengths of sides of a right triangle can't be negative, but when you deal with angles and quadrants, their sides can be negative. So while this big angle is actually A, technically, this angle right here is not A. That angle is actually the reference angle for A. It's A hat is what we'd call that. But don't worry too much about that. That's not that big of a deal. What is important is that you at least are able to write down the ratios. Now, you know, sine normally is opposite over hypotenuse if you're dealing with right triangles. Well, opposite of this green angle here, therefore should be, let's just write it as 3 for now, and hypotenuse of that green angle should be 5. One of them, because there's a negative here, has to be negative. Hypotenuse are never negative. That's one thing that you should be very aware of. That ray that emanates from the origin will never be a negative length. However, X and Y values can be negative, and in fact, in this case, because you're in quadrant 3, the Y value should be negative. So that tells us -3/5 is a sine of that green angle. Now I can use that if I wanted to, that triangle. In fact, I'll go ahead and draw out a triangle. Now, for all the mathematicians in the crowd, you might want to yell at me right now and say, you cannot have a side length that is negative. I totally agree with you. But remember, this triangle is supposed to be in quadrant 3, and that's why that side length is negative. Okay. Also, for all the mathematicians in the crowd, they will say, that's not your angle A, because that's an acute angle, and your angle A is actually greater than pi radians, which is a greater than an obtuse angle, actually. So I would agree with you 100%. However, I think trig is much easier to grasp for students if I just do it this way. Not that big of a deal. It really is not. Just as long as you keep in mind that your angle actually is in quadrant 3, and so that's why we're drawing our triangle this way. Technically speaking, it is slightly incorrect, but that's not a big deal. Honestly, don't worry about that. All right, so could we find this missing side right here? And the answer is totally, yeah, of course. Pythagorean theorem, this would be a length of 4. However, our angle is in quadrant 3, so the x value should be negative, so it should be a -4. So notice how I'm using my right triangle trig in conjunction with my point trig, or basically my non-right triangle trig, or you call it quadrant trigonometry if you want to call it that. Anyway, notice how I'm combining those two. It just makes the math a lot easier. Now, when I go back to this problem and I say, okay, what was I supposed to do? There was a lot of questions going on here. They're asking for the sine of 2a. Sorry, didn't mean to say it that way. Well, that's going to be twice the sine of a times the cosine of a. And luckily, we could just read those off of this triangle. Either of them. It doesn't actually matter. In fact, normally, I wouldn't even draw this green triangle. I would just keep it up like this, because that's a little more rigorous. And I would say, okay, well, what's the sine of that angle? Opposite over hypotenuse, that'd be -3/5. So this will be twice -3/5. And then the cosine of that angle, well, the cosine is going to be adjacent over hypotenuse. That's -4/5. Fill that in, -4/5. And now we can just do a little bit of arithmetic. You don't want to leave it just like that. So that's twice 12, or 24/25. There you go. Very fast, actually. While I did spend a lot of time drawing out a triangle and talking, the reality is once you get used to this, you will barrel through very quickly. These are very, very fast problems once you get used to them. The next one we're going to want to find is the cosine of the double angle. Now, there are 3 forms. All of them will give you the same answer. Let me just tell you what to do as far as a wise choice. They're all good choices, by the way. Now that we've drawn this out, they're all good choices. However, let's just pretend we just started this problem. Let's just pretend that. And somebody said, hey, the sine of A is -3/5. And then they say, I need to know what the cosine of 2a is. Well, if all I had, and that's a big if, because the reality is I've already drawn it out, but let's pretend that I didn't draw it out. The cosine gives me choice here. It gives me 3 choices for the cosine of the double angle. And one of those, specifically this one right here, involves just the sine of A. And they've given me the sine of A. So without even drawing a triangle, I could actually just figure out what the cosine of double angle is by using the identity 1 minus twice the sine squared of A. And we know that the sine of a is negative 3 over 5. So that's 1 minus twice negative 3 over 5 squared, because it's the sine squared. And then some arithmetic, right? So that's negative 2 times 9 25ths. And that would be 25 25ths minus 18 25ths, or in other words, 7 25ths. And you could have done this problem in any of the other ways. I could have instead done the cosine of the double angle using cosine squared minus sine squared of the regular angle. And that would require me to have already drawn out my triangle, which I did, so that's pretty nice. The cosine is negative 4 over 5. So I'll fill that in. That would be equal to a negative 4/5 squared minus. And then again, had I drawn out the triangle, the sine would be opposite over hypotenuse, negative 3/5. And so I would plug that in. Lots of moving around here. Negative 3/5 squared. And when you compute that, that's 16 25ths minus 9 25ths, which is the same thing as 7 over 25. And note, that is the answer we arrived at a moment ago. So it's the same no matter what you do. They're the same answer. It's just, if you want to work with both cosine and sine, then you would do this second version. If you just want to work with sine, you do the first version. And I think that shows you like an economy of computation. You can really optimize and speed up computation if you take advantage of what you're given. In this case, we are given the sine, so I just plug that in. Finally, we're asked for the tangent of the double angle. And I don't need a formula for that, because the tangent of the double angle is the same thing as the sine of the double angle over the cosine of the double angle. This reduces this trig problem down to an arithmetic problem, because the sine, as we see above here, is 24 25ths. I'll write that in. And the cosine is 7 25ths. And that is a compound fraction. I'll just multiply numerator and denominator by 25, and you'll get 24 sevenths, which does not reduce, and we're done. So those are our answers. I'll just highlight them. Sine of the double angle is 24 over 25. The cosine of the double angle is 7 over 25. And finally, the last one that we just did, tangent of the double angle is 24 sevenths. Very nice problem, and one of my favorite styles of problems to do, mainly because as we move forward, there's going to be a lot of little things that you can add on to this. For example, I could have in the future done a sine of a half angle, something like that. And there's quite a few other permutations of this. Now, on this second problem here, and we still got another problem, or have another problem to go through, but on the second problem, it says simplify this statement. And if you look at that, you might, if you don't know the identities, you might look at this and say, I don't know what to do with this problem, until you look back at your identities and realize that this actually does have a form similar, not exactly the same as, but similar to one of our identities. Specifically, and it's not exactly this, but it's close, the tangent of twice an angle is equal to 2 times the tangent of the regular angle. Let me zoom in so that I can actually write here. Tangent of the regular angle over 1 minus the tangent squared of the regular angle. Now, I did mention in the previous video when I introduced these trig identities, the double angle identities that is, that I don't have my students memorize the double angle identity for the tangent. However, it is nice to remember that it kind of has a form like this. So when I'm handed something with a bunch of tangents, I would probably think, well, maybe that's an identity for a tangent. Let me look that up really quickly. So just to let you know, this style of question is not super common, but in a standard trig class, it can come up. So be aware that you have to be, aware that this, because it has a bunch of tangents in it, is likely a tangent identity. So it's probably a double angle identity, or maybe a sum of angles identity. It's actually the same thing as a double angle identity. So anyhow, notice they're not exactly the same though, because this one, the identity has a 2 in it, and the problem we're handed doesn't. But a very common tactic in mathematics is to force something you want to be true by multiplying by 1. So I'm going to multiply this expression here by the number 1. So the number 1 is 2 over 2. You might think, why is he multiplying by 2 over 2? Well, it's very simple, because I would like to get a 2 in that numerator, because if you look at the identity to the right, I need a 2 in the numerator. So this is going to be the same thing as 1/2 times 2 tangent of 3 pi over 8 divided by 1 minus tangent squared of 3 pi over 8. Very, very common tactic. Again, I wanted to get a 2 in the numerator, so I forced a 2 in the numerator, but by doing that, if I only put a 2 in the numerator, I would have doubled this, and I don't want to do that. So I put a 2 in the numerator, but I also multiplied the outside by 1/2, so those 2's would cancel. We know that this picture can be traded out for the tangent of twice whatever these angles right here. Oops, that is not a highlighter, that is actually a pen. So anyway, it's twice these angles. So we're going to trade out this picture for the tangent of twice 3 pi over 8. So it's going to be 1/2 tangent of twice 3 pi over 8. That's an arithmetic problem. So 2 times 3 pi over 8. Let me zoom in a little bit. 1/2. It's being left-handed that does this. Tangent of 3 pi over 4. And now I know I could just use my base trigonometry skills, right? The reference angle for 3 pi over 4 is pi over 4. And I happen to know that that 3 pi over 4 is a quadrant 2 angle, and the tangent in quadrant 2 is a negative. So I can trade out that tangent of 3 pi over 4 for a negative tangent of its reference angle, pi over 4, and just write it this way. And tangent of pi over 4 is 1 over root 2, so this is negative 1/2 times 1 over root 2, and now we have a negative 1 over 2 root 2. For those who have instructors that force them to rationalize denominators, you can multiply the numerator and denominator by square root of 2. But I don't force my students to do that if you just have a single term in that denominator. I just leave it like this. This is done. All right. So that is the tangent of 3 pi over 8 minus, or divided by 1 minus the tangent squared of 3 pi over 8. It's just negative 1 over 2 root 2. The final example in this video is just going to be kind of a computational one here. If x is equal to 5 times the tangent of theta, write the following expression in terms of just x. So again, we're told that x is 5 times the tangent of theta, and we want to rewrite theta over 2 minus the sine of twice theta over 4. We want to write that in terms of only x. Now this is a calculus style problem. You face these problems in calculus quite often, in fact. And so you need to be able to work with these. The hardest part of this problem, I think, is honestly working with that theta. Rewriting theta in terms of just x. Well, if you take a look at what we were handed, we're told that x is equal to 5 tangent of theta. Well, if I want to find out what theta is, I'll divide both sides by 5. So we get x over 5 is equal to the tangent of theta. And then I will take the tangent inverse of both sides. Of course, when you take the tangent inverse of both sides, you're very much restricting what theta can be. Remember, tangent inverse or the arc tangent, or the arc trig functions in general, they return angles, but they're restricted angles. So I'm going to make a little note here. I'm going to say where theta is between negative pi over 2 and positive pi over 2. That's incredibly important to write that down. It's not that that is exactly the restriction they handed us, because that's actually not true, but this is what we're dealing with. And in fact, they didn't state it in the problem, but I'm just going to go ahead and add that into the problem. I'll say assume that theta is between negative pi over 2 and pi over 2, because it's an unfair question if I don't state it that way. So we'll just go ahead and make that assumption. All right, that being said, that just means that your angle is either in quadrant 1 or quadrant 4. That's not that important right now, because I just want to showcase I'm going to trade out this theta for this theta. In fact, for this picture right here. So let's go ahead and start that. This is equal to, instead of theta, I'll write it as a tangent inverse of x over 5 being divided by 2. And no, you cannot bring that 2 inside the tangent inverse. It's locked. So that is all, that's the only way, well, one of the only ways you can write it. You can actually write it as a 1/2 times the tangent inverse of x over 5 as well. And then we still have this minus sign of 2 theta over 4. But we happen to know the sine of 2 theta is the same thing as twice the sine of theta times the cosine of theta. Because we were not dealing with a double angle here. Nobody told us what 2 theta was equal to. All we know is what theta is equal to. Now, my warning to you is the following. I will have students, especially in calculus, who've learned trig a bad way. I will have students say, oh, well, theta's tan inverse of x over 5. And they'll throw into these thetas here, the tan inverse of x over 5, and leave it like that. That is terrible. The right way to do this is to go to this piece right here. Let me showcase what I'm talking about. The right thing to do is to go to this and say, okay, great. I know the tangent of my angle theta is x over 5. Remember, tangent is opposite over adjacent. So the opposite of my angle will be x, and the adjacent to my angle will be 5. And also remember, our angle is either in quadrants 1 or 4. Let me just showcase that. I have an angle in quadrant 1, and its opposite is x and its adjacent is 5. Or my angle terminates in quadrant 4, and its opposite is x and its adjacent is 5. Notice their adjacent sides are the same here. They should be the same. They should both be positive 5 because it's quadrant 1, x is positive, or quadrant 4. It is the x value on the x axis, but unfortunately the variable x is being used for the altitude here. Kind of confusing. I totally get it. But anyway, the horizontal sides are positive in quadrant 1 and 4. And now what we need to do, since we are being asked what's the sine of theta and what's the cosine of theta, right here, what we need to do is go ahead and use the Pythagorean theorem on both of these to figure out what the hypotenuse is. Well, Pythagorean theorem will tell us the hypotenuse is of length 25 plus x squared. In both cases, if you look down at the quadrant 4 version, it's 25 plus x squared. Now people will ask, wait a second, what if they're different? And my response is they won't be. They'll be the same. You'll be perfectly safe here. You're totally fine. So now we can go ahead and use either of those, doesn't actually matter, to read off what the sine of theta is and the cosine of theta is. So let's go ahead and go back here and we'll say this is equal to 1/2 tan inverse of x over 5 minus 2 goes into 4 twice. So I'm just going to go ahead and write this as 1/2. And now we're going to deal with the sine of theta. The sine is opposite over hypotenuse. So x over the square root of 25 plus x squared. So times x over the square root of 25 plus x squared times the cosine. And the cosine is going to be adjacent over hypotenuse, or 5 over the square root of 25 plus x squared. 5 over the square root of 25 plus x squared. Now clean this up. This is going to be 1/2 tangent inverse of x over 5. You've done algebra, so you in the past, so you should be able to do algebra today. So this is going to be minus 5x over 2 times the quantity. Square root of 25 plus x squared times the square root of 25 plus x squared is 25 plus x squared. And that's pretty much as good as it'll get. I suppose you could factor out a 1/2 out of both terms, but you don't have to if you don't want to do that. That's totally fine. But that is that original expression, theta over 2 minus sine of 2 theta over 4, written in terms of just x. Again, the very first thing I did was say, well, I need to solve for theta because they're asking me what theta over 2 is. So I need to solve this equation for theta. When you solve that equation for theta, you have to use the tangent inverse, which restricts the angle to be between negative pi over 2 and positive pi over 2, which means that theta is between quadrant, or is in either quadrants 1 or 4. I then actually normally just draw triangles in quadrants 1 and 4 immediately. It's just a habit I have. And then because we know the tangent of the angle in blue right here is going to be x over 5, we know that opposite is x. Opposite to the angle is x, and adjacent to the angle is 5 in both cases. But I actually don't really need that quadrant 4 triangle because it turns out they'll be the same triangle no matter what. The ratios are all the same. So I kind of ignored that quadrant 4 triangle. But from that point forward, I just inserted what theta was into the first equation or equal sign there. And then I traded out using a trig identity, the double angle identity, the sine of 2 theta for 2 sine of theta cosine of theta. I did a little bit of simplification right there. And then I looked at my triangles to find out what sine of theta is, cosine of theta is. And then I did some simplification in the end. Very, very popular style of problem and necessary for any type of success in calculus as you move forward.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.